Hello, this is a talklet reviewing the construction of composite curves. In other words, extracting the temperature and enthalpy information from numerous hot and cold stream data in order to combine these in order to find targets for heat recovery. So, in a previous talklet, we introduced these concepts using just one hot and one cold stream. A hot stream needing to be cooled down from 240 down to 40 degrees C and losing 800 kilowatts of heat in the process, and we had a cold stream that started at 80 degrees C and had a target temperature of 205 degrees C and needed to pick up 1000 kilowatts in the process. And we saw that when we made these two lines overlap on a temperature enthalpy diagram, the overlap indicated the heat recovery. So here we are, we're making them overlap, and they overlap such that the hot stream and the cold stream would enter a particular heat exchanger, and the hot stream, having entered at 240 degrees, would come out at 140 degrees, losing 400 kilowatts of heat in the process. The cold stream, entering this heat exchanger at 80 degrees, would come out at 110 degrees Celsius and would pick up the 400 kilowatts of heat that the hot stream had left. Therefore, there was 400 kilowatts of heat transfer going on in this heat exchanger. So where they overlapped indicates a heat exchanger in which heat recovery is occurring, and we're getting that heat for free. Where they don't overlap represents the additional hot and cold utility requirements that are needed. So our cold stream, having come out at 110 degrees, still needs to heat up to 205. That requires an additional 600 kilowatts of heat, and that's supplied by hot utility, for example, steam condensing at 240 degrees C. Similarly, our hot stream, having come out at 140 degrees, still needs to cool down to 40 degrees C. We achieve that using some cold water, which takes away 400 kilowatts of heat. So where they don't overlap gives us the remaining requirement, or the targets, for hot and cold utility usage. What about, however, the more common situation of numerous hot and cold streams? Lots of hot and cold streams in a plant, some needing cooling, some needing heating. Let's consider, by way of illustration and example, 3 hot streams. So we have one with a flowing heat capacity of 4 kilowatts per Kelvin, and it needs to be cooled down from 240 degrees C to 40 degrees C, losing 800 kilowatts in the process, and there it is. We're going to introduce a second hot stream. There's the slope of the hot stream indicated by the flowing heat capacity of 4 kilowatts per Kelvin. Now we're going to introduce a second hot stream, this one with a flowing heat capacity of 10 kilowatts per Kelvin. It needs to be cooled from 180 down to 120 degrees C, so a temperature change of 60 kelvins. Each change requires it to lose 10 kilowatts, and so in total it has to lose 600 kilowatts of heat, and there it is, starting at 180 degrees, finishing at 120 degrees, losing 600 kilowatts in the process, and its slope being indicated by the flowing heat capacity, where the slope is equal to 1 over the flowing heat capacity. And as we've said many times, a larger flowing heat capacity means a smaller slope, because it means a smaller temperature change for a given amount of heat loss or gain. Finally, we have a third hot stream. This one has a flowing heat capacity of 2.5 kilowatts per Kelvin, and it's going to cool all the way from 280 down to 80 degrees C, so that's a temperature change of 200 kelvins. Each of those takes a loss of 2.5 kilowatts, and so a total enthalpy change, or enthalpy loss, of 500 kilowatts. And there it is on its diagram, and there its small flowing heat capacity gives us a large slope, So there's not much to this stream. It either has a very small mass flow rate or a very small specific heat capacity. Either way, because there's not much of it, there's a big temperature change for a given heat loss. So we've got our 3 hot streams. The total heat to be removed from these 3 hot streams is 800 from the first stream, 600 from the second, 500 from the third, giving a total loss of 1900 kilowatts. Now, in the context of heat integration, there are 2 things about heat that are important. The first is how much heat there is. How much heat is available in a hot stream, or how much heat is required by a cold stream. How much heat there is an important consideration. That seems obvious, that seems reasonable. The second important consideration is how hot that heat is, what temperature it's at, or how hot the heat that needs to be supplied needs to be at. So how much heat is available and what temperature that heat is at. These 2 things are important. Now, streams tend to change temperature when they gain or lose heat, so really we want to know how much heat there is over a particular temperature range. As a stream changes its temperature, how much heat does it give up, how much heat does it take up. But it doesn't matter if the heat in that temperature range comes from different streams. Heat at a particular temperature is equally valuable in heat transfer, heat exchange, heat recovery terms, wherever it comes from. So, returning to our 3 hot streams then, the important things are how much heat there is and in what temperature range that heat is. So we can add up the heat in particular temperature ranges from the different streams. So let's divide our graph up into temperature ranges which are dictated by the supply and target temperatures of our 3 streams. So starting from the lowest temperature range. The lowest temperature range indicated here is from 80 degrees C down to 40 degrees C, and there's just one stream that has heat available in that temperature range. That's our first stream. And the total heat available in that temperature range is equal to the flowing heat capacity of that stream, which is 4, multiplied by the size of the temperature change, which is 80 minus 40, 40 degrees C. 4 times 40 is 160 kilowatts. So there's 160 kilowatts of heat available at that temperature, or in that temperature range. Now for the other temperature ranges, heat is available over each range from more than one stream until we get up to the very top again, where once again we've just got heat at that very highest temperature just in one of our streams. But for the others, there's several possible sources of heat at that temperature. So let's add them up. So for the next temperature range, that's from 80 up to 120 degrees C, we've got 2 streams, the first one and the third one, that both have heat to give in that temperature range. The first one, the amount of heat that it has available is, again, it's got a flowing heat capacity of 4 kilowatts per Kelvin. The temperature change is 120 minus 180, so that's a total of, 120 minus 80, which is 40. So that again is giving up 4 times 40, which is 160. The third stream, it has a flowing heat capacity of 2.5. Again, a temperature change of 40 degrees. 2.5 times 40 is 100. Adding 160 and 100 together gives us 260 kilowatts altogether of heat available in that temperature range. Now, what we notice, of course, is the 2 components that we're adding, the temperature range is the same in each case, 120 minus 80. So we can combine those together such that we could combine the flowing heat capacities together. We could have 4 plus 2.5 times 120 minus 80. That we could add the flowing heat capacities. So let's do that for our next temperature range. Our next temperature range is from 180 degrees down to 120 degrees. All 3 of our streams are contributing over this temperature range, so we can add their 3 flowing heat capacities. For for the first one, 10 for the second stream, 2.5 for the third stream, which gives a total of 16.5. 16.5 times a temperature change of 60 gives us 990 kilowatts of heat available in that temperature range. Our next temperature range is from 240 degrees down to 180. Once again, we've just got two streams contributing in this range, the first stream and the third one. So adding their flowing heat capacities, 4 plus 2.5, gives us 6.5 times a temperature change of 60, gives us a total of 390 kilowatts. And then our very hottest heat, we've only got one stream at this very hottest temperature range of 280 down to 240. It's our stream with the flowing heat capacity of 2.5, so 2.5 times a temperature change of 40 gives us 100 kilowatts up at that highest temperature. Adding up all of these heat contributions, they total 160 plus 260 plus 990 plus 390 plus 100 gives us 1900 kilowatts again. We've still got the same amount of heat available in our three streams. It's still a total of 1900 kilowatts, but now we've divided that available heat up into different temperature ranges instead of dividing it into different streams, because it makes more sense to tabulate our heat in terms of how hot it is, rather than in terms of where it comes from. But it's the same amount of heat. We're just identifying it, dividing it up differently. We can put this information in a table. So here's a table, and we're going to identify the temperature, the relevant temperature ranges, the sum of the flowing heat capacities of all the streams in each temperature range, and then from that information we can calculate the total amount of heat available in that temperature range, and then in our right hand column we can add that up. So starting at the bottom, add up the total amount of heat available as we increase the temperature. So starting at the bottom, our bottom temperature range is 40 to 80 degrees. The temperature interval, the temperature change is 40 kelvins. We only had the one stream in that temperature range. Its CP was 4, so the sum of the CPs is 4. 4 times 40 is 160, and then to add up the amount of heat available, we start at 0. So by the time we get down to 40 degrees C, we're saying we've got 0 heat left. At 80 degrees C, we've got 160 kilowatts left. Right, similarly then, our next temperature interval from 120 down to 80, again the size of the temperature interval is 40 K. On this occasion, the sum of the specific heat capacities was 4 plus 2.5, which is 6.5. 6.5 times 40 gives us total heat available in this temperature range of 260. Adding that to the 160 that we already have, we have 420 kilowatts of heat available from 120 down to 40 degrees C. Right, our next temperature range, this is from 180 to 120, so the size of the temperature change is 60 kelvins this time. All three of our streams are contributing, so the sum of the flowing heat capacities is 4 plus 10 plus 2.5, which is 16.5. 16.5 times 60 is 990 kilowatts of heat. Adding that to what we've already got gives us a total so far of 1410 kilowatts. Similarly, our next interval, again, the temperature change in this interval is 60 kelvins. The sum of the CPs, once again, was 6.5, giving us a total of 390 kilowatts in that range. Adding that to what we've got already, and we're up to 1800 kilowatts. And then our final temperature interval from 280 down to 240. This is our hottest heat. How much is there? Not that much, because it's only one stream with a flowing heat capacity of 2.5. So 2.5 times 40 gives us a total of 100 kilowatts, and adding that to the 1800 that we've already got, we've got a total of 1900 kilowatts of heat from our three streams at all these different temperatures. And from this, the composite curve is now easily constructed. So starting from the bottom, 40 degrees C corresponds to no heat left. 80 degrees C corresponds to 160 kilowatts of heat left, and then adding up each of our curves. So by the time we get to 120 degrees C, we've got 420 kilowatts of heat available. At 180 degrees C, we've got 1410 kilowatts of heat available. At 240, we've got 1800, and at 280, we've got all of our heat, 1900 kilowatts, available. And the slopes of the different parts of our composite curve are once again given by the sum of the flowing heat capacities, reminding us once again that the higher the flowing heat capacity, the smaller the slope, because there's less temperature change for a given heat input or loss. So that's how we construct composite curves. Comparing with the original information, we remind ourselves where the heat in each temperature range came from. In each temperature range it was contributed by one or two or all three streams. Just to run through it again, let's do the same again for some cold streams. This time we're just going to have two cold streams. So our first has a flowing heat capacity of 5 kilowatts per Kelvin. It's being heated from 50 to 230 degrees C. There it goes, and it therefore requires 900 kilowatts of heat. We then, there's its flowing heat capacity. We then have a second stream. This has a much larger flowing heat capacity, 20. It needs to be heated from 110 to 150 degrees C, so 800 kilowatts of heat. So a much larger flowing heat capacity, therefore a much smaller slope, much less of a temperature change for a similar amount of heat. So in this case, the total heat that needs to be supplied to our two cold streams is 1700 kilowatts. Once again, we can add up the heat in particular temperature ranges from the different streams. Once again, the ranges are dictated by the supply and target temperatures of the streams. So here we go from the bottom. At the very bottom, our first temperature range is from 40 up to 110 degrees C. Just our first stream is requiring heat in this temperature range. It has the flowing heat capacity of 5, so the total amount of heat that we require is 5 times 60, which is 300 kilowatts. In our second temperature range, from 110 up to 160 degrees, both of our streams need some heat at this temperature. So adding the flowing heat capacity is 16 plus 5 equals 21. 160 minus 110 is 50. 21 times 50 is 1050 kilowatts. And then up at the hottest temperature range, our first stream needs a total of 5 times 70, which is 350 kilowatts at that highest temperature. Once again, the total amount of heat that's required is 300 plus 1050 plus 350, which is 1700 kilowatts. So it's the same amount of heat, we've just divided it into temperature ranges instead of dividing it into streams. Once again, we can tabulate the information and add up the total amount of heat that we require as we increase the temperature. And if you want, you can pause the video, the recording at this point, and do the calculations yourself just to check. Having tabulated the information, again we can easily construct the composite curve. We start at our lowest temperature of 50 degrees C with 0 heat at that point. By the time we get to 110 degrees C, we've required 300 kilowatts. By the time we get to 160 degrees C, we need a total of 1350 kilowatts. And then by the time we get to 230 degrees C, we need the full amount, 1700 kilowatts by then. Once again, the slopes of the different parts of our curves are indicated by the sum of the flowing heat capacities. And once again we can compare with the original information to see where the information in our composite curve has come from. Now, comparing the hot and cold composite curves, There they are, plotted independently. We can plot them on the same graph, of course. To do that, we'll move our hot composite curve to the right so that it ends at 0. And then we can move our cold composite curve wherever we like in relation to the hot composite curve. We can shift it horizontally as far as we like. We're going to shift it until the closest point of approach between the two gives a temperature difference at that closest point of 20 degrees C. So our delta T min, our minimum temperature difference between the hot and the cold curves, is 20 degrees C. This gives us an overlap that covers a range of 1600 kilowatts. So we're recovering 1600 kilowatts of heat potentially. If we can, having identified this overlap, if we can now design a heat exchanger network that delivers this, then potentially the maximum amount of heat recovery that we can get, if we design our network correctly, is 1600 kilowatts. Now, there's still some additional heating of our cold stream is required, and there's still some additional cooling of our hot streams are required. So in terms of the additional cooling of our hot streams, we still need 300 kilowatts of cold utility. And we need an extra 100 kilowatts of hot utility to finish off the heating up of our cold streams. But comparing this with the 1900 kilowatts of cold utility and the 1700 kilowatts of hot utility that we would require if we didn't have any heat recovery, we've saved ourselves an enormous amount of energy costs. We're only having to supply 100 kilowatts of steam instead of 1700 kilowatts. That's an incredible saving. That's well worthwhile. So as we've said previously, the scope for heat recovery is much greater when you've got many hot and cold streams to consider. So this indicates the thermodynamically feasible targets for minimum hot and cold utility, which we call QH min, the target for minimum hot utility, and QC min, the target for minimum cold utility. And we're saying this is thermodynamically feasible. If we've decided that a delta T min, a minimum temperature difference of 20 degrees, is appropriate, that will give us heat exchangers that aren't too large, then having made that decision, this is the maximum amount of heat recovery that you can possibly achieve. This is the minimum amount of hot utility and cold utility that you can possibly require. So for our particular example, the minimum amount of hot utility is 100 kilowatts. The minimum amount of cold utility is 300 kilowatts. And if you design a heat exchanger network that delivers this, that gives you only 100 kilowatts of steam usage or hot utility usage and only 300 kilowatts of cold utility usage, then you know that you've done the best that you can. You know with confidence that your heat exchanger network couldn't be any better. It's as good as it can be. Alternatively, if you design a heat exchanger network that requires more steam or more cooling water than this, then you know that you're doing something wrong and you've missed an opportunity for heat recovery. Now, often we want to calculate the amount of heat recovery. Note that it can easily be calculated as the sum of the hot stream loads minus the cold utility. So in other words, all of the heat that we had to lose from the hot streams, some of that we've lost into cold utility, the rest we must have recovered. Or alternatively, the sum of the cold stream loads minus the hot utility. In other words, all of the heat that we had to supply to the cold streams, some of it we're supplying from steam, the rest we must have supplied from hot streams, we must have recovered. That makes sense. So, for our particular example then, Q recovered is the sum of the hot streams, which we remember our hot streams had 1900 kilowatts of heat that we needed to get rid of, minus the cold utility, which we've identified here as 300 kilowatts. So 1900 minus 300 is 1600 kilowatts, which is indeed the overlap that's shown on our graph, 1600 kilowatts. So that's correct. Or alternatively, the sum of the cold streams, we remember that, was 1700 altogether, minus the hot utility, which is 100. 1700 minus 100 is also 1600 kilowatts. So we can calculate the heat recovery easily using either of these calculations, and preferably using both. If they both give the same answer, then that's a useful check that we haven't made any mistakes in our calculations. As we've said before, the nice thing about heat integration is the calculations are simple. They're simple additions and multiplications. But they do need to be done accurately. It's easy to make a mistake in doing these calculations, and having these sorts of checks, just making sure that our heat recovered comes out the same through both calculations. Doing those sorts of checks is just a good idea to make sure that you haven't made any silly mistakes. Now, the point of closest approach of the composite curves, we've identified previously that we call the temperature difference at this point delta T min, and that's an important choice that the designer has, the choice of delta T min to get the balance between capital cost and energy costs. But the point where delta T min occurs is called the pinch. So there it is on our diagram. The pinch is occurring at that point. The temperature difference at that point is 20 degrees. The temperature of the cold streams at that point is 110 degrees C, and the temperature of the hot streams at that point is 130 degrees C. So there's the pinch, and that's the pinch is an important concept. So in summary then, construction of composite curves is achieved by summing the available heat within the temperature ranges defined by the supply and target temperatures of the streams. So we look at the streams, the supply and target temperatures that they have, and from those we work out what the relevant temperature ranges are that we need to tabulate our information in. This is equivalent to summing the CPs within each temperature range and then multiplying by the range. Composite curves can be moved horizontally relative to each other to give a point of closest approach at the required value of delta T min, and the point where this occurs is called the pinch. The overlap between the composite curves at a given delta T min indicates the theoretically thermodynamically feasible heat recovery, and where the curves don't overlap indicates the targets for hot and cold utility, and having those targets, that gives a confident basis for proceeding with and evaluating heat exchanger network designs.